Part F, use suitable calculations, determine the third harmonic current at resonance, and use it to determine the voltage across the capacitor and inductor. Now, because the two are the same, the magnitude of the voltage. Alright, what we can do, so we're on F, we go at resonance, Z3, so Z at the third harmonic, which is the resonant frequency, R plus XL minus XC3 on both of those, J as at Z3 XL equals XC, Z3 equals R. So you're showing that you know those two terms are going to cancel out, and therefore the only impedance left behind is the resistance R, which is 4 ohms. We can then go, therefore, current at resonance equals V3 over R, which is 220 over 4 equals 55 amps. Sorry? As at Z3 XL is equal to XC, Z3 equals R. That's all that's left. They cancel each other out. Okay, and then also the VC is equal to VL in magnitude at least. They're opposite in angle, but we're interested in the magnitudes here. Equals I at resonance times XL or XC, doesn't matter, 3 equals 55 amps times 5.895 ohms equals 324.5 volts. Okay, here, because the resistance is significantly low, or like an ohm or less than an ohm, the increases, the original current in this problem of 30 odd amps, 30 amps or so, is not a huge difference, but it's still 25 amps on top. If you think of this circuit being designed to not have, designed only to have, go back to the first page, only to have that voltage, 560, and not have any harmonic on there. All of that is unwanted. We'd only get 30 amps, and now we're getting 55 amps just from the third harmonic waveform. That's without the bit from this added on the top. So if the circuit's been designed for 30 amps, and you start passing 55 amps, it's not going to be good news. Okay, and some examples are more graphic than that, because the voltage at the end ends up in the thousands of volts as opposed to the 500 or 200 volts we started with. Okay, and if you notice, I'll answer your question in a minute, Dom. I'll listen to you in a minute. For the final part in the actual question in the exam, there'll be 3 further marks for you understanding the effects of the calculated harmonic currents and voltages on the components of the circuit. Right? So I'm not going to go through that for you to remember root form. Think about what more current can do to a circuit. What about more voltage across a capacitor, and so on. And to write just a short piece about that, so you'll understand and what that could mean to the components of that circuit. Yeah? Boom, sometimes. Yeah? I mean, if you think about it, the capacitor would have been designed for 560 volts here anyway. But what you must remember, where we calculated in the second part that voltage, that's the voltage due to the unwanted third harmonic. The voltage due to the fundamental across that component could be added or taken away from that at any point in time. Yeah? Alright? Just, I want you to think about what could happen to the components that are in the circuit. So maybe 3 or 4 lines would be my stock answer. Right? I have been, but I'm not gonna give you a worked answer with it all written out on. Dominic. Question 2. You've been given a diagram like so, with a square waveform like so, between -1 and 2, between minus pi and pi on the T line. Yep, and this is volts. And it says that square wave can be represented by the Fourier series in the form of, and I'm not going to write it all on the board, but it's the Fourier series, okay, with the coefficients AO, A1, A2, B1, B2, etc. In order to demonstrate this, carry out the following calculations. For the square wave shown, write the 2 functions of t that represent it between pi, minus pi and pi. So this is A. Because we've got a discontinuity here, we have to express this as 2 separate parts. Yep, and deal with them as 2 separate parts. So that's what. The way we do that is to say Vt equals -1 when t is between minus pi, t is greater than minus pi, less than 0. Yeah. Sorry. When it's 0, that's where the discontinuity is. But for the values, for the, if you wanted to, you're going to integrate in a minute to get the area there. So your limits are minus pi and 0. Yeah? Okay. So there's two parts to this definition. It equals 2 when 0 is less than t and t is less than pi. So that's what part the question's looking for, and that would give you a couple of marks, I expect. Not sure, I haven't put the marks on this question. Right, B, it says, show that the DC component of the series A0 is equal to 0.5 volts. Right, we've got the formula which you'll be given in the exam. A0 is 1 over 2 pi times between pi and minus pi v t dt. That's the formula that you are given. Yeah. But what we have to do is we have to apply that to the two functions and add them together. So effectively what we're saying here is IO is equal to 1 over 2 pi times, so we can keep that constant outside some brackets, the integral between O and minus pi of minus d plus the integral between 0 and plus pi of 2 dt. Close the brackets. That equals 1 over 2 pi big set of brackets. When we integrate this, what do we get? Integrate minus 1. Need your table of integrals really, which will be in the exam. Yeah, our variable of integration is t though, so be minus t between minus pi and 0 for that one, plus brackets two t between 0 and pi. Close the big brackets. Yeah. This is minus 0 minus pi. Because it's minus t minus pi is plus pi. Yeah, agree with that? Yeah. That's that bit. Take away 2 pi minus 0. I've got all the brackets. No, because when you... That should be plus, yes. Shouldn't it? This bit is that bit, and this bit is that bit, and they're added together. Correct. Well spotted. IO equals 1 over 2 pi times pi equals 1 over 2 equals 0.5 volts. Yep. Well, 0 is 0, but I just put that in there for completeness. But the result of that bit is what is minus pi plus 2 pi equals pi. Yeah, so that's pi, 1 over 2 pi is that bit outside the brackets, and that pi is all what's in it. Yeah, everyone happy? Right? Part 6 says, show, using Fourier series formulae and standard integrals provided, show that the power series does not contain any cosine terms. Yeah. So, the A terms are the cosine terms apart from AO, so we got the formula AN is 1 over 2 pi and when we've got to do each function separately again, do 0 and pi of minus 1 dt plus 0 pi plus 2 dt. That's the calculation we've got to do from the formula to find the IN, and N being the A terms being the cosine terms. Wait a minute. Whoa, I haven't done that right now. Sorry, boys and girls. That should be minus 1 cos t dt plus integral between 0 and pi of 2 as well. Alright, so if we take A1, sorry? This is minus pi, yeah. There? Yeah. So, if we, as 1 over pi, big set of brackets, we integrate the cosine minus cosine, we get yeah. A1 is 1 over pi this bit is minus sine O minus sine of minus pi plus brackets 2 sine pi minus 2 sine O, like so. Yep. Now, sine of 0 is sine of minus pi is but minus the sine of minus pi. There it is. Yeah. Just check this bit in these two brackets. There's that bit there. Yeah, and that's the upper bound integration take away from the lower bound. Yeah. Hang on, that's 0. Sine of minus pi is 0. Here we go. 0, pi over 2, pi, 3 pi over 2. Sine of pi or sine of minus pi, whichever way you take it, is 0. Sine of 2 sine pi is 0. 2 sine 0 is 0. A1 equals 0. Yep. And the only difference we're going to make if we go A2 is this number's going to be nothing's going to change the fact that those signs are always going to make all those numbers in there 0. Yeah, it is clear because we're working with here. We're working with sine n times pi, because as we go up we put an n in front of that t. So for this example there's a 1 in there, but when we find I2 that will become cos 2t, cos 3t, and so on. This number outside here become 3, 4, 5, 6. It's always going to equate to 0. Yeah. So the statement that needs to go in there is something along lines, clear that sine of any number n pi equals 0, and sine minus n pi equals 0 for any value of n. This means no cosine terms. Because the formula is looking at the for IN, because the formula for IN is VT times cos NT, N being the number of the constant you're trying to find, because that doesn't matter. Once you have integrated, you're always going to be multiplying by a 0 term, and are all going to calculate your constant 0. So there's no cosine terms in the complex waveform representing this square wave. Right? D. We've got the formula Bn is equal to 1 over pi integral between pi and minus pi of Vt sine Nt. That's the formula we're going to use. Okay. B1 1 over pi integral between minus pi and 0 of minus 1 sine t dt plus integral between 0 and pi of 2 sine t dt. Close the brackets. Yep. So if we integrate minus sine t, we end up with cos t. I'm going to add that to -2. All happy with that? Expand on that 8 further still. Okay. Right, what's the cosine of 0? Cosine of minus pi. -2 times the cosine of pi. And this one is so we've got 1 pi 1 minus -1 plus 2 minus -2. What are they equal? 1 minus -1 is 2. Yep. 2 minus -2 is 4. We want a 6 of a pi. Yeah. So we enter the two integrals separately into the formula. We integrate them both. Expand. We've got cosine of 0 minus cosine of minus pi plus curly brackets minus 2 cos 2 pi minus 2 cos 0. Yep. We've got to come over 2 here as well. Because these are the 2. As Ben was saying earlier, when you do this, that's 1 over A, and A is 2 here. There's 1 over A out here. So the whole thing is over 2. Yeah, got it? Cos 0 over 2 minus the cos of minus pi over 2. Where? Minus 2 pi. Correct. Yeah. Right. Cos of 0 over 2 is a half. Cos of minus 2 pi over 2. Yeah, there's a minus in there, and that's 1 over 2, hopefully. Yeah. And this, minus 2 cos 2 pi over 2. I've got minus 1 for that. Yeah. And we're minus, and that's minus 1. Yeah. So overall, those 2 equal 0, and those 2 equal 0. B2 equals 0. Yep. Again, because we can say that because cos 4 pi cos minus 4 pi cos 6 pi cos minus 6 pi, and so on, all evaluate to 1. This will be true for all even terms of n. So there'll be no B4, no B6, no B8, and so on. So from that point in the question, If you can realise that, you don't have to calculate any others. All right. And I'm prepared to reflect on how many I'm asking you to do here. And if this is a question, I won't ask you to do as many of these. Don't go on anything more. Okay. That would be the DC component. Prove that there aren't any evens, as in this. Prove there aren't any cosine terms. And two terms. Right. Cosine of 4 pi is 1. As is cosine of minus 4 pi, 6 pi, minus 6 pi, and any even number times pi, they all evaluate to 1. So they'll all be like this. 1 over 4, 1 over 4, 2, 1 over 6 for the 6, 1 over 8, 1 over 10. Whichever even end term you pick, they're going to cancel out. When n equals 3, B3 excuse me. I mean, in all truth, once you're done one, that's putting the other different numbers in it, isn't it? Sorry? Well, no, it's not pi over 6 divided by 3. Yeah? Oh, hang on. Actually, yes, it is, because you'll turn that one up the other way. The answer is 6 over 3 pi. Hang on, because we're doing 6 over pi. 1 minute. Correct. Yeah. Well spotted, that lady. Yes. In terms of if you correctly show that you know that's what it means, you can do that.
So if we write B3 for 6 over pi,
yeah, which comes out as 6 over 3 pi.
B3 is always going to be B1 over 3.
My problem with that is if, and I'm only going to give you a square wave, but my issue with it is if that weren't a square wave, that wouldn't be the case. Because we're doing a square wave, right? Listen, because the square wave, the amplitude of each waveform in the Fourier series reduces by the number of the n, right? That's not necessarily the case if we were talking about a sawtooth or a triangular waveform. So there's a danger in saying that's always multiplied by 3. Yeah. All right. So that is the danger. All right. So just going to go through, just quickly go through the calcs here, all right? And I'm kind of missing out a step here because I'm going to integrate straight away. So that's cos 3t over 3 between minus pi and 0. It's okay to jump those steps because you've shown them all in the earlier example. And this is going to be 3 that's minus 2, sorry. Yeah, minus 2 cos 3t over 3 between 0 and pi. Yeah, so I've integrated it straight away rather than writing all that other stuff out. Okay, and therefore B3 is 1 over pi times cos 0 over 3 minus cos minus 3 pi over 3 plus minus 2 cos 3 pi over 3 minus 2 cos 0 over 3. Yep. They evaluate to that one as a third. Minus a third. Right or not? And that bit evaluates to 2 over 3. Yeah. Minus 2 over 3. Cos of 0 is 1. Minus 2 times 1 is minus 2. All of that evaluates to be equal to 1 over pi times 2/3 plus 4/3 equals 6 over 3 pi. And we run out of time, so cut it short. B5 is equal to, what do you reckon? B7 would be, and so on. therefore, we can represent V, T approximates to 0.5, the DC term we calculated in the first place, plus 6 over pi sine pi over 2 hang on, no, sine t, sorry, plus 6 over 3 pi sine 3t plus 6 over 5 pi sine 5t. And for the last bit of the question, where it asks you at pi over 2, the answer is 1. Just before we go, we'll freeze that up there. Graph that waveform. You can see even after those two terms, it's approximating to the DC that we had in the first place. Across there. Across there. Yeah. So add in further terms, and this ripple on the top here will decrease. And if you include an infinite number of terms, you have the perfect sine wave. Yep. Sorry? No, you're not expected to do that. No. It's just to show you that that does start to approximate to the square wave we were trying to represent. That's all. Yeah. Okay. If you look at this square wave, right, it will, if you rotate it 180 degrees around that midpoint there, that'll come back on itself. So if I could take that waveform, pick it up and do that with it, this line and come down here, if that will do that, then you only get sine terms. Yeah. If there's our axis, if there's a reflection about the y-axis like that one is, you only get cosine terms. And if you haven't got either of those, you'll get both. You'll get sine and cosine terms. Right?